Imagine a world where motion is powered not by fuel, but by the invisible dance of magnetism and spin. Today, we're diving into the quantum spin dynamics of a magnetic motor, a machine that defies the ordinary and might just be the key to a new era of energy. These devices are not just engineering marvels. They're a bridge between classical physics and quantum mechanics. The spin of electrons, the alignment of magnetic domains, and the subtle quantum fluctuations all play a role in how this motor moves. The core of its operation lies in the quantum spin dynamics, how particles at the atomic level interact and transfer energy through spin states, creating a continuous, self-sustaining motion. This isn't just about moving metal. It's about understanding the fundamental forces that govern matter and how they might be harnessed in ways we've never imagined. In the next beat, we'll unravel how these spin dynamics are modeled, and whether this motor is a real breakthrough or a tantalizing mirage of physics. So what exactly are we talking about? We're discussing a magnetic motor, but not the kind you find in your car or a washing machine. This is a system designed to exploit the quantum spin dynamics of magnetic particles, where subatomic spins align and interact in ways that challenge classical physics. At its core, the motor operates by using the intrinsic spin of electrons or atomic nuclei. These are tiny, fundamental particles that behave like tiny magnets. When their spins are aligned, they create a magnetic field. And when they're not, they generate interactions that can be harnessed for energy. The goal of this motor is to create a continuous, self-sustaining motion by leveraging these quantum interactions. In theory, it could lead to devices that generate mechanical motion or electrical current without an external power source, which is why it's so intriguing and controversial. However, it's crucial to distinguish this from perpetual motion machines, which are impossible under classical physics. This is about tapping into the quantum realm where new phenomena arise, and the rules of energy conservation may not apply in the same way. In this video, we're not just talking about a gadget. We're exploring a frontier where quantum mechanics meets engineering, and where the spin of particles could one day power the next generation of machines. Magnetic motors aren't just about perpetual motion. They're a gateway to understanding how quantum spin dynamics shape the fabric of reality at the smallest scales. When you look at a magnetic motor, you're actually peering into the quantum realm, where spins interact and influence each other in ways that defy classical intuition. By studying magnetic motors, you're unlocking secrets of how quantum spin controls energy transfer and magnetic order, keys to next-gen tech and fundamental physics. The spin of particles isn't just a curiosity. It's a fundamental aspect of nature that defines the behavior of everything from atoms to the cosmos. Understanding these spin dynamics is like learning the language of the universe. Once you speak it, you can decode the rules that make reality tick. Let's rewind to 1927, when quantum mechanics was still finding its footing. Schrödinger's equation and Heisenberg's uncertainty principle set the stage for understanding spin dynamics at the quantum level. By the 1950s, Pauli's spin matrices became the foundation for modeling quantum spin, offering a mathematical structure that could describe particles' intrinsic angular momentum with precision. As the 1970s progressed, the concept of spin-orbit coupling emerged, showing how a particle's spin interacts with its motion, adding layers to the quantum spin dynamics picture. By the 1990s, quantum spin dynamics became a key player in fields like spintronics and quantum computing, where spin states are used to encode and process information. Today, we see the legacy of that early work in everything from magnetic resonance imaging to quantum algorithms, all built on the foundation of quantum spin dynamics. Imagine a spinning top, but instead of just spinning, it's also dancing with invisible magnets. This motor doesn't just rotate. It's like a tiny ballerina twirling with invisible strings. These invisible strings are actually forces from magnets pulling and pushing the top. It's like the top is caught in a dance with invisible partners, making it spin in new ways. The motor's secret is that it's not just spinning. It's also spinning in different directions, like a ballerina twirling while also spinning around her own axis. This special kind of spin helps the motor keep going without needing extra power. It's like the top finds a way to keep dancing without tiring. So the motor doesn't need batteries because it's using the invisible dance of magnets to keep spinning. It's like a tiny magician who never runs out of tricks. To begin, the magnetic motor's core is a carefully arranged array of permanent magnets, each with a precisely defined polarity and orientation. These magnets are mounted on a circular rotor, ensuring rotational symmetry and balanced magnetic forces. Surrounding the rotor are stator magnets, strategically placed to interact with the rotor's magnetic field. These are fixed in position, creating a stable magnetic environment that allows for dynamic spin interactions. The entire system is enclosed in a non-magnetic housing to prevent external interference. This housing is designed to allow free rotation while containing all internal magnetic interactions within a controlled space. A power source is connected to the rotor, typically a low-voltage DC supply, which initiates and sustains the rotational motion. The interaction between the rotor and stator magnets creates a continuous magnetic torque. This initial rotation is the first step in the quantum spin dynamics of the motor. The rotor's spin state becomes entangled with the magnetic field of the stator, initiating a cascading effect of quantum interactions. Now, the second step involves the interaction between the magnetic poles of the rotor and the stator. As the rotor spins, its north and south poles pass by the fixed magnets of the stator, creating a dynamic field alignment. This interaction generates torque, which is the rotational force that keeps the rotor spinning. The torque is sustained by the continuous reorientation of the magnetic field as the rotor moves. The key to this mechanism is the precise arrangement of the stator magnets. Their placement ensures that the magnetic field is always in the correct orientation to apply torque to the rotor at the right moment. This torque is not just static. It's a result of the continuous magnetic induction between the rotor and stator. The motion is self-sustaining, as the magnetic field reconfiguration keeps the force applied in the right direction. In this stage, the system operates on the principle of magnetic flux coupling, where the motion of one magnet induces a force on another, maintaining the cycle of rotation. Now, the clever twist comes in when the rotor's angular momentum begins to couple with the magnetic field's orientation. This coupling isn't random. It's a carefully engineered interplay between the magnetic poles and the spinning inertia of the rotor. The key is that the rotor isn't just spinning. It's rotating in such a way that its magnetic field is constantly reorienting itself. This creates a kind of feedback loop between the rotor and the stator, which is essential for sustained motion. By carefully tuning the magnetic field strength and the rotor's rotational speed, we can induce a kind of quantum coherence in the magnetic domains. This coherence allows the rotor to maintain a stable, low-energy spin state that persists over time. This coherent spin state is what gives the motor its efficiency. It allows the rotor to maintain motion with minimal external input, as the quantum coherence effectively reduces energy loss through magnetic resistance. In essence, the clever twist is not just mechanical. It's a quantum-level manipulation of magnetic spin states, which allows the motor to operate beyond the limits of classical magnetic dynamics. At the heart of this system lies quantum spin dynamics, a phenomenon where subatomic particles, like electrons, align their spins in response to magnetic fields with extraordinary precision. These spin states don't just flip. They interact through quantum entanglement, creating correlations that defy classical intuition and enable energy transfer at an atomic level. This is not classical mechanics. It's a dance of quantum states where the motor doesn't just move. It oscillates in a way that defies traditional energy conservation laws. By harnessing this spin coherence, the motor achieves a level of precision and efficiency that classical systems can't replicate, unlocking new frontiers in energy and motion. Imagine a spinning top, but instead of just spinning on its axis, it's also flipping its own magnetic poles like a coin that keeps flipping midair. Each flip is a quantum spin transition, and it's all happening in a dance of forces we can't quite see. This top isn't just spinning. It's in a constant state of quantum wobble, where the direction of its spin isn't fixed, but probabilistically determined by the magnetic fields around it. This isn't magic. It's a quantum mechanical system, where the spin isn't a simple rotation, but a superposition of states, like a spinning coin that's both heads and tails at once. So, in a way, the magnetic motor isn't just spinning. It's performing a quantum ballet of spins and flips, all dictated by the unseen forces of magnetic quantum dynamics. This analogy is dumb, yes, but it's accurate in its simplicity. It captures the essence of quantum spin in a way that feels almost like a child's toy, yet it's rooted in real physics. Before you go, if you enjoyed this, please give it a like and subscribe so you don't miss the next one. And tell us in the comments what you'd like us to make next. We read every single one. Thank you so much for watching. Comment this emoji if you made it to the end.